Oh, hello everyone, my name is John Aspinall and I work for Hydek Consultants in Leeds, and today I'm going to be talking you through the evaluation of a distribution chamber via CFD. So first of all, I'm going to give you a quick introduction into what the company is and what my role is within the company. Then I'll talk you through a quick description of the scheme, then the reason why we're testing it, followed by a description of the modelling technique that we used, and then an assessment that we obtained of this distribution chamber, followed by the data that we obtained, and then proposed work that we recommended, that we advised. So first of all, Hydek is primarily a modelling company. We specialise primarily in CFD and physical models. So CFD is using a computer numerical analysis of various systems where we simulate fluid flow and interaction of this fluid with other fluids and structures. The second type of models that we carry out are physical models, where, as you can see here, you've got an example of two distribution chambers. The physical model is built out of perspex, clear perspex, so you can see within the model, and then the grey is called formex, and then this is also used to simulate fluid for particular type of structures. So my role there is a test engineer, and we recently got a speculative inquiry from a client where they were concerned with a sewage treatment works, and they decided they were going to repurpose an existing station to turn it into a distribution chamber because of tightening of effluent limits due to the effluent from this treatment site being discharged into a river. So we're worried about the effluent conditions, and also due to the tightening because of the new water framework directive, and because this station needs to meet current and future standards. Also, because of the increase in collective population, they asked us to carry out an assessment of an existing structure. So the two primary areas they were concerned with are velocities within the chamber. This is because the phase of the treatment that they were concerned about is process of the flocculator, where water is dosed with magnetite and then flocks form, which is an exceptionally useful process for eliminating particulate matter from the water itself. So they found that the industry standard for flocks which will be within water be dosed with magnetite has to be within 0.3 and 0.6 meters per second. If it drops below, the flocks will drop out the water within the chamber. If they're above, these flocks will break up. Another concern of theirs is the distribution of flow within this chamber. So it contains 3 different weirs, and they want water to spill across each weir to a certain target, and it has to be with plus or minus 5% of this target. So we had an internal discussion within the company as to how we're going to approach this, CFD or physical model, and I recommended that based on the data that the client required, so velocities and a flow split, the fact that they were under time constraint, they required information quickly and efficiently and reliable, I recommended a CFD model would be perfect for this situation. The reasons being are that a CFD would allow us to provide velocity values throughout the entire water volume, throughout the entire chamber, and a flow split as well. It is much more cost effective and time effective as well compared to a physical model. We will be able to obtain results from the CFD model before the physical model would actually have even been built. Also has a much lower environmental impact because we could build the entire structure and simulate it within a computer. We would not require to use any materials. I see from the image beforehand, we require timber frame and plastics as well to build the model, and then not to be dismantled and discarded. And also, well, we could meet all of their requirements by doing a CFD study. So how the CFD study was conducted? Well, first we created a 3D model geometry from drawings provided by the client. Then this geometry was meshed. A mesh is basically a series, or the entire structure, the entire system is divided into millions of cells, and then this mesh is imported into a software called ANSYS Fluent, which numerically solves the Navier-Stokes equations along the boundaries of those cells, and it gives us a simulation of the fluid flow. The fluid, of course, the flow is turbulent, so with this a K-epsilon turbulence model is included, and this model was then operated transiently, which means it's constantly changing until a fully steady state was reached, and from that steady state then from those results the data was abstracted and used. The chamber has a series of inflows, well, 3 different inflows, a minimum 280 litres per second, a maximum of 633 litres per second, and then an average of 332. The chamber has 2 different inner pipes which are joined together at a T section, so the required flow over each weir for each inflow scenario were 93, 110 and 211. So finally you can see this is the model geometry that was used. Now you might be wondering why there are 2 pumps within the chamber. It is distribution chamber, but that's because this is an existing structure on site. It is currently used as a RAS return, so water enters the station and is then pumped out. They're now to try and reduce costs, time, and make sure that they don't have to build any newer structures. They can repurpose this as a distribution chamber. These holes here are the weirs, and the model was set so that we have 2 inlet boundaries where the velocities within the pipes, the velocities were set, and this is a T section I was talking about. The reason the boundaries are set on these 2 pipes away from the T section is because this would have the biggest impact on how flow entered the chamber itself, and then water build up into the chamber and spill over the weirs. So the outlet boundaries were set just past the weirs to make sure that there was fully free discharge and that they weren't affecting what occurs in the chamber itself. So these are other views of different points of views of the 3D model. And now in terms of results, so at maximum flow we found, this is a velocity contour plot from the CFD analysis, and that's a table containing the flow split for all 3 inflow scenarios. Let me see, based on the velocities, the velocity across within the water across each weir was quite comparable, but as we analysed the data we found that the inflow was well within plus or minus 5%. The biggest differential was the maximum flow of weir 3, where it was lower, was about 1.8% lower than the target. So flow split within the chamber was exceptionally good. Very happy with that. The issues appeared with velocities. So these are velocity contour plots. We got, the first one is streak lines, and then the others are contour plots on slices through the chamber, and the color scale is logarithmic. This is because we wanted to have a very good idea of what the velocities were like below 0.3 meters per second. Now, flow from the inlet pipe, which is about mid-height of the chamber, entered the chamber, tracked across the top, hit the back wall. We found that then it formed recirculation zones, and at maximum flow, and if you can tell from the plots, the velocities were very high within the inlet pipe and very close to the exit, and then these remained reasonably high at about 0.3 meters per second, at least across the back of the chamber and the base. As you can see from the last plot as well, there was velocities from the cells close to the floor, but these recirculation zones formed where velocities weren't high enough, and this would cause issues where the flock could then start to settle and would then be re-picked up by the high velocities and recirculated, but that could extend residency time within the chamber itself and then not leave, then be transported to final settlement tanks. This at average flow rates, because the water volume remained the same but inflow of course reduced, then remained comparable. and inflow reduced, found that velocities of course reduced as well, and that was nowhere near the minimum required. So flock would start to settle at the base of the chamber and then collect the bottom and not actually be carried to the final settlement tanks. This of course occurred at the low flow rate as well. So at the end we found from our analysis, from the CFD analysis and the data obtained from it of this distribution chamber, we found that velocities ranged quite a bit from 0.04 meters per second up to a highs of 1 meters per second. Of course, for the low and average flow rates, velocities towards the back wall and the base weren't high enough, so flock would definitely settle and then collect at the bottom. But for flow split, for the distribution of the flow, and it was well within the specified limit. The issue is finding a solution to stop the flock from settling. So I discussed with other engineers within the company who have worked with other distribution chambers and other flocculators what solution they think for this specific scenario would be suitable. We came to a conclusion that there would be different methods. One could be to insert more benching into the chamber, so reduce the volume overall, which will increase velocities. The issue is that this is a current structure and that it has to remain in operation. So I discussed it with the client if this would be suitable. We then determined that it would be impractical to adopt and it would be problematic in terms of health and safety. So we found a different solution, which is the use of a large blade propeller that could be installed whilst the chamber remains in operation. It could be fixed at the top on the surface, lower down into the chamber about mid-height. This large blade propeller wouldn't spin fast enough to destroy the flock, to break up the flock, but has a wide range effect within the chamber itself and could provide higher velocities. I do need to mention that this is from a different chamber. This is for a flocculator itself, a different project, but it's just indicative of how it can be used to improve velocities. So in the end, this project has given me a broader idea of distribution chambers, pumping stations, and what practical aspects that we can actually find when it comes to projects, and whether or not an idea could be suitable and can actually be carried out or not. An example would be the reduction of volume, provision of benching. We thought it would be a good enough solution, but then discussing it with the client, it was actually impractical because they couldn't actually access the base, or it was due to health and safety reasons and continuing functioning of the treatment works. It was impractical. So this is an ongoing project. This hasn't been tested yet, and that's the next stage. In the next week or so, we'll find out whether or not it is a suitable solution. Any questions?